Welcome back, ladies and gentlemen. Today we're going to talk about section 5.3, properties of angle bisectors in triangles and creating an incenter. Up on the screen, as usual, you will see your exit question for the day. I'm going to start off the day today with a theorem, theorem 5.5, which is the angle bisector theorem. We already know what an angle bisector is. We're just now going to give a theorem to help us out with a couple drawings. So if we have an angle that is being bisected and we have a point on that bisector, so point D is what we're talking about, then the angle bisector theorem says that point D is equidistant from each side of the original angle. Now remember that when we talk about the distance between a point and a line, that distance is always measured on a perpendicular path, and that's something you're going to need to remember. So in order to use these theorems, both this and the converse, which is coming up on the next slide, it needs to be measured along a perpendicular path. So if you have an angle being bisected and a point is on the bisector, then the distance between that point and the sides of the original angle are congruent. Likewise, we have a converse, which basically just says the converse of what we just said, which is if you have some random ray, or not even a ray, just a point that is equidistant from each side. So if you measure the distance from the point to the side of the angle and you find those distances to be the same, then we know that D must exist on the angle bisector. We can use both these theorems to figure out a couple simple problems. Why don't you pause the video right here and try to figure out the answers to these. On this first example, this illustrates the most common mistake made in this section, which is, hey, we've got two equal distances, so S must be on the bisector. Well, not quite true, because this angle right there is not marked as a perpendicular angle, so that means that this may or may not be the exact distance between S and R. Or, well, it is the distance between S and R, but it may not be the distance between S and ray QR. So make sure that you're always looking for that perpendicular symbol right there. So lots of words to explain that one, but that's basically the gist of it. It needs to be measured along a perpendicular path. Finding the value of x, super easy on this one. These are marked as being equivalent measures, so you know that the distances, and they are marked as being perpendicular this time, must be the same, so x must be 15 by theorem 5.5. Likewise here we have, again, congruent distances, and we know that they're distances because they're marked as being perpendicular, so now we can safely set those two angle measurements equal to each other and solve for x. And now that we can use these theorems, I'm going to show you a construction with a triangle involving angle bisectors and what properties fall out of that. So here I am again in GeoGebra, and I have my polygon tool selected here, and I'm just going to make a random triangle, nothing special about it. And I am going to construct the angle bisectors of each angle by selecting 3 points, and you'll notice that it'll cut the angle in half of whichever 3 points I choose. And if I do all three of that, you guessed it, you're going to get another concurrent point where all 3 angle bisectors intersect each other, and we have our second type of point of concurrency for this chapter. They will always be there, so they always intersect each other at exactly 1 point. And unlike the circumcenter that we talked about in section 5.2, you'll notice that the location of this point of concurrency, called an incenter, is always inside the triangle. No matter if I have an obtuse triangle, a right triangle, or an acute triangle, the incenter, this point of concurrency, always occurs within the triangle. Now for this next step, my drawing is going to get a little messy, but basically what I want to do is I want to draw a line that is perpendicular to one of the sides of the triangle right here, that is perpendicular to this line and goes through this point. So I'm going to grab this tool again to help me draw a perpendicular line. It's going to ask me to select a point and a line, and you'll see that it'll draw a new line. It's not the same as this bisector because now I'm locking in that angle right there to be perpendicular, but must go through that point. I'm going to repeat that 2 more times, and you can see how messy the drawing starts getting, and it gets very confusing because I don't know which one's my bisector and which one's my perpendicular line. So I'm going to pause this for a moment, and I'll come back to you with everything nice and labeled and clear looking. Okay, you can see now that I have my drawing cleaned up. I've kind of trimmed off the edges here, and I still have my 3 angle bisectors here in black, but those 3 new segments that I was talking about that are guaranteed to be perpendicular to each side are here highlighted in blue. And you'll notice that as I move around the triangle, those segments remain perpendicular, and the importance of that perpendicular property to them is that this is now defined as the distance. So if we wanted to find the distance between the incenter and a side, it would be the length of this segment. Now, you might notice as I move these around that there is something pretty interesting about those three segments, and that they all appear to be approximately the same length. And if I scoot it off to the side, there's kind of an optical illusion that makes one look longer than the others, but if you actually go through it and measure it, you can actually verify that they are the same length. Furthermore, if I wanted to prove it to you, I could just simply draw a circle right there. I can draw an inscribed circle inside of the triangle that intersects all 3 points that came about from us just measuring the distances between the incenter and the side of the triangle. So there's a couple properties to remember here. That one, if you construct the angle bisectors, you will get a point of concurrency. That point of concurrency is equidistant from the sides of the triangle, not the vertices like the circumcenter. And of course then that allows us to inscribe a circle within the triangle. Also, last important point here is that the incenter is always contained within the interior of the triangle. And that brings us to some of the properties of the incenter. First off, a definition: a point of concurrency constructed with angle bisectors of a triangle. That will result in it always being located in the interior of the triangle, and our book gives us a little theorem to help us out. The important part of that theorem is that the distances between the incenter and the sides of the triangle are all equivalent. And then lastly, I showed you in the construction there that it is possible to inscribe a circle inside of the triangle. Using these, we can of course do some more geometry problems. And here it is. So copy down the drawing and the given information and see if you can figure out what the length of ND is. The first thing you need to notice is that ND, there's no numbers over by it, but ND is the same length as NE and NF. So if you know NE or NF, then you also know ND. And we can see right here that we have a triangle that we know 2 out of the 3 sides of, and it appears to be a right triangle. So first intuition is that we need to identify that the 3 blue lines are equal in length because it's an incenter. And then secondly, we need to recognize that this is a right triangle. ANF is a right triangle with a hypotenuse of 12 and one side of 16. So simple Pythagorean theorem will do the trick here. Set it up, solve it. NF is 12, which means that ND is 12. And it's really that simple. Up on the screen, you'll see your homework for the next day. Again, we're going to do a construction in class and on your assignment, so bring a compass and a straight edge.